Hello everyone, welcome to lecture 33 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be on bistable nematic displays. Here is the lecture outline. We'll have a brief recap from ferroelectric to nematic bistability. Then we'll talk about the 5 bistable nematic LCD variants, their shared traits. We'll focus on twisted untwisted bistable nematic BTN, the 360 degree device, discuss about the hydrodynamic switching mechanism and the backflow effect, their optical design and transmittance optimization equation for BTN, and then we'll look into the BTN driving schemes, 1 phase, 2 phase and 3 phase. After that we'll move on to surface stabilized nematic liquid crystals, the zenithal and azimuthal bistable designs, and finally we'll establish a bridge to bistable cholesteric reflective displays. So here is a brief recap from the previous lecture where we covered SSFLC, that was basically having 2 planar smectic C states addressed by DC pulse polarity. Switching was governed by a voltage time area law. So today we begin the second bistable liquid crystal family. We'll talk about the bistable nematic liquid crystal displays. So here no smectic layering is required. So the bistability will now come from hydrodynamic flow effects or from engineered surface anchoring rather from the ferroelectric symmetry. So what is the reward of doing this? The reward is that the nematic materials are far more common, cheaper and easier to process as compared to ferroelectric smectics. So cost wise, as with SSFLCs, you will see that most bistable nematic displays will also have to pay a price by not being able to provide any native grayscale. Okay. So it's only basically on off. So let us now introduce the bistable nematic LCDs. So there are basically 5 practical bistable nematic variants: twisted untwisted, that is BTN, zenithal bistable, azimuthal, that is surface induced bistable, then you have mechanically bistable, and you have bistable STN. That's basically bistable super twisted nematic. Okay. Now a bistable nematic material has 2 stable states with different optical properties. Once driven into a state, it will basically stay there. That's why it is called bistable. There are 2 and it is stable on each state. So these materials can be used on a purely passive matrix with no information content limitation in principle. Now what are the shared strengths across this family of bistable nematic variant is that these are common, easy to process nematic materials. They can provide high contrast ratio and also can support wide viewing angle. However, there is a recurring drawback as was there with SSFLC. I already mentioned that this kind of bistable nematic LCDs cannot offer grayscale capability. So now let us start by going into the details of each one of these families members, like twisted untwisted bistable nematics, that is BTN. So these are also called 2-pi bistable LCD. Okay, so as you know that there are basically 2 stable states. They are basically twisted by phi and phi plus 2 pi respectively. Okay, so here phi is basically the substrate's relative rubbing angle. Okay, and phi, the value of phi can basically range between minus pi by 2 to pi by 2. So the 2 bistable states are basically selected by exploiting hydrodynamic motion of the liquid crystal. Okay, So this basically the same coupling between the director rotation and fluid flow which was covered earlier. Now let us consider the first case of phi equals 0, that means the parallel rubbing. So in that case, the two states are basically 0 degree twist and 360 degree twist, okay, as you can see here. Now if you consider chiral dopants, okay, they basically set the intrinsic pitch P, or you can say H by P. H is basically the cell thickness, that will be half. So that will make the true energy minimum in that case of 180 degree twist state, okay, which is here, okay, not the 0 or 360 degree state. So what you can understand that the 0 and the 360 degree states are basically therefore metastable. That means they are locally stable, addressable, and they are long lived, but they are not the global minimum. So this is exactly the topologically protected bistability that the display basically exploits. So these are basically the liquid crystal director configurations of the BTN states with 0 degree, 180 degree, 360 degree, and this is typically the homeotropic. Now we'll go into the details of this hydrodynamic switching and learn about the backflow effect. So this BTN switching basically explodes the two-way coupling between the liquid crystal's director rotational motion and the fluid flow, that is the backflow motion. So for low field, that is just above threshold VTH, so here a shallow homeotropic region basically forms only in the cell midplane, and upon removal it basically relaxes to a 0 degree state. So it has got the same topology with 0 net twist, and at high field, that is above the saturation of VSA, okay, so above the voltage, saturation voltage. So a deep homeotropic state basically forms everywhere, and on sudden removal a faster surface relaxation versus slower mid cell relaxation that happens, and that mismatch basically drives a translational hydrodynamic motion that basically pushes the till ankle further. So what you understand that with intrinsic chirality being present, that flow carries the director all that way to the 360 degree state. Without it, that means you have a chiral case, you will see that the same flow only produces a temporary distortion that can decay back, and that is the typical backflow phenomena. So the practical constraint here is that switching to 360 degree needs both a sufficiently high field and a sufficiently sudden removal, and you will see that a slow removal or residual bias voltage will basically leave the liquid crystal in the 0 degree state instead. So how do you design this bistability? The bistability of the twisted untwisted design has been experimentally observed for this phi angle, rubbing angle between minus 90 degree to plus 90 degree. Now the design rule that links the cell thickness, pitch and the rubbing angle is here. So the phi plus pi twist state must be the true energy minimum that we have already discussed earlier. We have seen that 180 degree state is the energy minimum. That basically gives you that 2 pi into h by p will basically become phi plus pi. So a related device with 0 degree and 180 degree bistable twisted nematic. So these are the two things. So here this will instead choose a chiral dopant concentration, so that you will find 0 degree and 180 degree states to have equal energy. So in that case you can have the two states between 0 degree and 180 degree. So with one strongly anchored tilted layer and one weakly anchored planar layer, this 0 degree 180 degree devices addressing pulse can be shortened to microseconds. So this is how they are related, as I mentioned. So 2 pi into h by p. So h is the cell height, p is the pitch, the liquid crystal, and then this is the twist angle phi plus pi. So now let us look into the optical properties and see the general transmittance formula. So for a uniformly twisted nematic with twist angle phi, okay, the entrance exit polymer or polarizer angle is considered to be alpha I and alpha O in and out, okay, and the total retardation is tau, and the transmittance that you actually can find out, that follows the standard twisted nematic Jones matrix formula, okay. So you can write T phi equals cos square alpha O minus alpha I minus phi minus sin square theta sin 2 alpha O minus phi into sin 2 alpha I minus phi square by theta square. We will see what is this capital theta all about, sin square capital theta, and then you have cos 2 alpha naught minus phi into cos 2 alpha I minus phi by 2 theta sin 2 theta into sin 2 alpha O minus alpha I minus phi. So this is the equation that gives you the transmittance, where you are basically defining the capital theta as square root of phi square plus gamma by 2 whole square. So this is a combined phase parameter that appears throughout the transmittance expression that you can see, and this phi is basically the total phase retardation calculated as 2 pi by lambda difference between the extraordinary and the ordinary refractive indices multiplied by the cell gap or the cell height. So this is exactly the same general transmittance formula that was used for ordinary twisted nematic displays. So here the bistable twisted nematic optics basically use no new optical theory, only a different set of stable twist angles, okay, that is the phi needs to be basically plugged in into this formula. So let's see how we can optimize this 0 360 degree BTN and obtain the best contrast. So you can set the entrance and exit polarizers at plus 45 degree and minus 45 degree. That means you can set alpha I as 45 degree and alpha O as minus 45 degree. And then for the 0 degree twist state, that is phi equals 0, you can actually reduce that transmittance equation from the previous slide to T0 degree to be sin square gamma by 2. And for 360 degree twist case, okay, you need to put this phi equals 2 pi, so that will give you T 360 degree. That comes out to be sin square root of 2 pi whole square plus gamma by 2 whole square. Now you can see this basically depends on both the gamma and the 2 pi twist term. So if you plot the difference in the transmittance, that is T 0 degree minus the T 360 degree against the retardation, that is gamma by phi, okay. So you will see that this basically peaks roughly near every gamma equals 2 pi, okay, and the best peak was obtained here, that is around phi equals 0.97 into pi, and around this one, that is around 6.92 pi. So what does it means? Higher phi basically needs a thicker cell or a larger delta n, and the designer basically picks whichever practical peak basically fits. So what is a good design choice? You can see you can take gamma to be 0.972 pi. That will give you T0 degree as 0.998. That is very high transmission, 99.8% transmission, and T 360 degree to be only 0.033, that is only 3.3% transmission. And if you go for the second best peak, this one, you can actually get slightly reduced bright mode transmission. So it is 98.6% here, but your 360 degree will be almost 0. So the other alternative design for this bistable twisted nematic can be a minus 90 degree and 270 degree also. So here you are basically choosing phi to be minus 90 degree. Okay, that gives a bistable pair at phi equals minus pi by 2, that is minus 90 degree, and phi equals 3 pi by 2, that is 270 degree. So in this case the polarizers can be set at minus alpha I equals alpha O will be 48 degree. That means you can say that alpha is basically minus 48 degree and alpha is basically plus 48 degree. So you will see that the optimum retardation in this case gamma will be 2 root 2 pi, and in this case the design basically achieves a dark state in this minus 90 degree twist angle, that is T minus 90 degree will give you 0 transmittance, that is the dark state, and T at 270 degree will give you a bright state with 96.5% transmittance. So this shows that the bistable twisted nematic optical design is basically flexible. So you can change the polarizer angle, the twist angle and the phi. This all can be adjusted together to hit a desired or target contrast. So in this case these are the equations which comes out to be when you put these values in. So T minus 90 degree will be cos square, and then you have square root of pi by 2 whole square plus gamma by 2 whole square, that's to the power root 2, which I already mentioned as square root. Similarly T 270 degree will be cos square root of 3 pi by 2 whole square plus gamma by 2 whole square. Now the question comes, how do you drive a BTN matrix and what are the design requirements for that? So you can see that bistability alone does not guarantee the multiplexibility. So you require a proper drive scheme that needs to be engineered around the BTN specific hydrodynamic switching physics. So the requirement is very straightforward. You require first addressing speed, low drive voltage, there should not be any pixel to pixel crosstalk, and a simple waveform to generate. So three drive scheme families basically exist for the bistable twisted nematic, which are classified by number of addressing phases: 1 phase, 2 phase and 3 phase. So each additional phase generally buys higher speed, but at the cost of more elaborate waveform. Okay, that will be discussed in this particular slides. So let us look into the 1 phase and the 2 phase drive scheme. So one phase, so here the figure shows, first figure shows the 1 phase and this one shows the 2 phase drive scheme waveforms. Okay, so these are the voltage waveform with time, and this is the transmittance, how it changes with time for both the cases. So let us focus on the 1 phase first. So here a single pulse amplitude basically decides our outcome. So when here you can see the VL basically gives the shallow, okay, that is the low twist pathway, and VH gives the deep or high twist pathway. Okay, so how it works, the 1 phase addressing works like this. So the selected row will get this VL plus VH by 2, so that is called the VRS. So the VRS voltage of VL plus VH by 2 will be applied on the addressed row, and you will give 0 volt elsewhere. However, the limitation here is that per line the delay is around 10 millisecond. So it is too slow beyond very low information content. Okay, you cannot use this, right? Now let us look into the 2 phase. Okay, here what happens, you basically have a long reset of around 10 millisecond that drives rows to deep homeotropic phase. Okay, and then you follow it with a short selection of 1 millisecond. So you are basically giving a very short selection pulse of 1 millisecond, so where the VL or VH basically decides the final twist. So here this is basically how it works. This is basically your reset pulse, okay, the reset phase VR, and then you can give the selection phase VL or VH to basically do the selection of the final twist. So this reset does not decide the outcome. So many rows can be reset in parallel, so that are basically pipelined, and only the selection is basically sequenced. So what is happening? The selection time is only 1 millisecond. So that is how this two phase is basically becoming faster. Now if you think of the three phase, it basically adds another delay phase in between the reset and the selection phase. So in reset, what is happening? You are having high field, so you are getting the deep homeotropic, and then you have this delay where you have zero field, so your liquid crystal is basically relaxing freely, and after that you apply the selection pulse, that is either a VL or a VH. Now because liquid crystal already begins relaxing during the delay phase, the selection voltage only needs to steer the late stage of an in progress relaxation rather than controlling it from the very beginning. So that basically shrinks the phase selection duration to as little as something like 100 microsecond. So what is happening? You are basically able to pipeline the reset and the delay phases across many rows, and you can then only apply 100 microsecond of selection per row. So that means this three phase addressing can basically reach the genuine video rate speed. Now with that we understand how these things work, the bistable twisted nematic. Here we will look into a second nematic bistability mechanism. Okay, we will talk about the surface stabilized nematic liquid crystals. Okay, that means a different route altogether. So the second nematic bistability mechanism engineered the alignment layer surface itself rather than relying on bulk hydrodynamic flow. So there are two categories. One is zenithal bistable twisted nematic. Here the bistability is in the surface tilt angle, and there is azimuthal bistable twisted nematic where the bistability is in the in plane anchoring direction. So both of these basically use micro structured alignment layer gratings or groups to create two locally stable anchoring configurations at zero fields. Now because bistability lives at the surface rather than in the bulk flow, these designs can retain their image even under mechanical squeezing, and this is an advantage BTN's hydrodynamic mechanism does not share. Okay. So let us look into this zenithal bistable or Z bistable nematic liquid crystal. So the structure was done by Brian Brown and others. Okay. So one substrate has this homeotropic alignment, the other one is non-symmetric grating, okay, made by oblique UV photolithography, right. So here you can see the two bistable states nearing the grating surface. Okay. So this two stable states basically exist near this grating at zero field. So one is a high tilt, another is low tilt. So these are distinguished by opposite sign ferroelectric polarization from director band, right. So how the switching takes place? So a high voltage of one polarity relaxes to high tilt state. The opposite polarity basically relaxes to low tilt state. So the cross polarizer at 45 degree to the groups will give you bright state. That means you are basically having low tilt and your gamma is phi, versus dark state or dark phases from the high yield states. Okay, and the pulses as short as 100 microsecond are possible in this case also. So you can get a video rate capacity. So this is how the formula looks like. Okay, here you can basically see the two panels basically showing the detector's band deformation near the group surface for high tilt and low tilt states okay, with the induced ferroelectric polarization vector P. You can see here P, okay. So, that is basically pointing in the opposite direction in each case, and this is the flexoelectric. So, you can see this flexoelectric formula. It basically it decomposes induced polarization into a splay term, okay, that is proportional to n times the divergence of n, and then there is a band term, okay, that involves the curl of n, okay, and near this grating geometry the band term will basically dominate and its sign differs between the two states, okay, which is what a voltage of a correct polarity basically exploits together with the ordinary dielectric coupling. So, this figure shows the azimuthal bistable nematic liquid crystal. So, these are the bigrating alignment and the two director states. So, bistability in this case lives in the in plane, that is azimuthal anchoring direction rather than the surface tilt angle. So, these are called azimuthal bistable nematic liquid crystal. So, how it is done? So, oblique SiO evaporation onto the substrate twice, okay, and you ensure that the blaze directions are rotated 90° to each other, and that can produce this bigrating alignment layer, okay. So, the resulting surface basically anchors along two directions with different pre-tilt. So, plus 45° with non-zero pre-tilt and minus 45° with 0 pre-tilt, okay, and the non-zero pre-tilt basically has a splay deformation inducing a flexoelectric polarization, okay, that is pointing up in one state and pointing down in another, okay. So, a DC voltage of the correct polarity can basically select between them. So, here you can basically see the schematic of a top down or a top down view that shows the two blaze or groove directions and the two resulting stable director states, each leveled with its easy axis and induced polarization. So, these are the easy axis marked and the induced polarization is leveled here. So, the explicit parallel back to the Z stable design here is that whether the bistability comes from a band deformation near the grating that was seen in the case of zenithal, or a splay deformation that is coming in this case of asymmetric pre-tilt, okay, for the case of azimuthal, the switching principle basically remains the same. So, a flexoelectric polarization difference between the two states, as you can see here, lets an applied DC voltage of one polarity or the other, okay, select which state this cell relaxes into. Now, if you compare the three nematic bistability mechanism, the first one, the BTN, that was hydrodynamic, okay, that was the fastest with the 3-phase drive. So, we have seen 100 microsecond per line, so it can support video rate, but the mechanism is sensitive to squeezing since it basically relies on bulk flow. Then we discussed this zenithal bistable, that is Z bistable, where flexoelectric switching at the grouped surface. Here also 100 microsecond pulses and video rate capable, and these are mechanically robust. And the last one we saw was the azimuthal bistable, where flexoelectric switching via bigrating in plane anchoring was possible. So, this was equally robust like the Z bistable with much simpler structures, because here you just have single grating type fabrication logic. So, all three, like SSFLC before them, they still lack the native grayscale, and this is the big limitation that only cholesteric family which will be discussed in the next lectures, they will be substantially able to overcome through multi-domain memory, right. So, here is a summary that we understood in this lecture, that BTN can achieve 2 pi bistability via hydrodynamic backflow with optical contrast, that is optimized through polarizer angle and retardation design. There are 3 driving schemes for BTN, that is 1 phase, 2 phase and 3 phase. These are basically progressively pipeline the waveform to reach video rate addressing. Then we discussed about zenithal and azimuthal bistable nematic crystals. Instead, they can achieve bistability at an engineered surface which are switched by flexoelectric coupling, but they actually provide better mechanical robustness as compared to BTN. Okay, and this basically completes our discussion about the bistable nematic displays. In the next lecture, we will talk about the bistable cholesteric reflective displays. So, this is the third bistability mechanism, and these are based on helical structures, and we will be covering these details in depth in the next lectures. So, with that we conclude this particular discussion. If you have any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.